Welcome. In this lesson, we'll be reviewing how to simplify radical expressions. So let's get started. Well, for the first question states, is there any relationship between the following expressions? Pretty much, can we simplify any of the following expressions? And once we do, can we say any relationship among them? Well, let's start with A. We know that the square root of 5, it cannot be simplified. So the square root of 5 is just the square root of 5. But when it comes to the square root of 20, notice that 20 can we break down into two values, 4 times 5. But why do we want to break it down into 4 times 5? Well, when we want to simplify radical expressions, we always want to simplify it as a multiple of numbers that we might know the square root of. But notice that we do know the square root of 4. So that's why we could have simplified 20 as 10 times 2. But notice that we don't know the square root of 10, neither the square root of 2. So when we want to simplify radical expressions, we always want to simplify as a multiplication of at least one number that we know the square root of, such as 4 or 9 or 25 and so forth. But once that we have written out this way, notice that we could just, this is equivalent to just the square root of 4 times the square root of 5. But we do know what the square root of 4 is. The square root of 4 is 2. So now this just becomes 2 times the square root of 5. Now, taking a look at example C. Again, is it possible for me to reduce the square root of 45? Again, I want to ask myself, can I multiply two numbers where one of those numbers I do know the square root of 4? But notice that 45, that is equivalent to 9 times 5. 9 times 5 is 45. But notice that I do know what the square root of 9 is. So now I can just rewrite this as the square root of 9 times the square root of 5. And we definitely know how to simplify this. The square root of 9 is 3. So now this just becomes 3 times the square root of 5. Taking a look at 80. Again, we want to see, can we simplify the square root of 80? Well, I can see that 80 can be written down as 16 times 5. But now notice that I'm always choosing numbers that I do know the square root of. In this case, we knew what the square root of 4 was, square root of 9. We do know what the square root of 16 is. But once I have this, notice that I can just rewrite this expression as just the square root of 16 times the square root of 5. We do know what the square root of 16 is. The square root of 16 is just 4. So now this becomes 4 times the square root of 5. But now we have not answered the question, is there any relationship between the following expressions? Well, the relationship is that they're all multiples of square root of 5. This is 1 times the square root of 5. This is 2 times the square root of 5. This is 3 times the square root of 5. This is 4 times the square root of 5. So in this case, they're all, the relationship among these 4 examples is that they're all multiples of the square root of 5. All right, well, let's keep going. Now, recall that, and we kind of already did this on the introduction question. It says to simplify radical expressions, we want to take a look at the root of the radical and the exponent of the inside of the root. If the root is multiply of the exponent, we can definitely simplify it. But what do we mean by this? Well, let's take a look at example 1. Can we simplify the following expressions? And if yes, then let's do it. Well, again, the square root of 25, you might already know this, that the square root of 25 is just 5 itself. But why is it that the square root of 25 is 5? Well, because notice that 25, we can rewrite this. 25 can be written out as 5 to the second. So therefore, the square root of 25 is just the square root of 5 to the second. But one thing that we kind of take for granted is that every time we just write down square root of, there's always an invisible 2 there. Always. If there's any other number as a root, then we use that number. But anytime that we write down the square root, we always assume there's an imaginary 2 there. But now notice, okay, coming back to our example. Now notice that the root, which is 2, and the exponent of the number that is on the inside, which is also 2, what this rule is saying is that whenever the 2 match out, then they will cancel out. And therefore, my result is just 5. So in other words, the square root of 25 is just 5. All right, let's take a look at another example. The square root of 75. Is it possible for me to simplify the square root of 75? Well, let's see. 75 first. Can I write it as a multiple of one of the numbers that I do know the square root of 4? Well, I know that the square root of 75, I can see 75 as just being 25 times 3. And now that I know that 25 times 3 is equivalent to 75, I can just rewrite this expression as just the square root of 25 times the square root of 3. Whenever you multiply two numbers inside the square root, that's equivalent to just multiplying the square root over the numbers. But I already know that the square root of 25 is 5, so now this just becomes 5 times the square root of 3. So we were able to simplify it. So the square root of 75, that's just equivalent to 5 times the square root of 3. Now looking at 500, well, the first thing you want to ask yourself is, okay, let's concentrate on the inside. Is it possible for me to rewrite 500 as a multiple of two numbers where I do know the square root of one of those numbers? Well, I can see that 400, I can just rewrite this as 100 times 5. But notice that I'm using 100 because I already know what the square root of 100 is. That will be 10. So let's just rewrite our expression. This is also equivalent to just the square root of 100 times the square root of 5. And we do know what the square root of 100 is. The square root of 100, that's just 10. So now this becomes 10 times the square root of 5. Notice that the trick here is, well, always try to rewrite the inside of the square root as a multiple of numbers that you do know what the square root of is. Well, if we take a look at example D, well, first things first, let's write down some numbers that I do know the square root of. We definitely know the square root of 4, which is 2. We definitely know what the square root of 9 is, which is 3. The square root of 16, which is 4. The square root of 25, which is 5. And I can actually stop right here. Could notice that, okay, we want to write down 14 as a multiple of numbers that I do know the square root of. In order that 14 cannot be written as 14, we cannot write it down as 4 times something, because 4 times something, and we just want to use whole numbers, we cannot find a multiple of 4 that is equivalent to 14. And the same goes with 9. There is not a whole number where we can write down as 9 times something equals 14. There can be a decimal, but we want to use whole numbers here. So therefore, notice that 14, it cannot be simplified. 14 does not have a multiple of some numbers that we know the square root of. So in this case, we cannot simplify. Looking at 35, okay, let's take a look at 35. Is it possible for me to write down 35 as a multiplication where one of those numbers I do know the square root of? Well, these are the numbers that I know the square root of so far. I mean, there's more than that, but we just want to stop at 25 because I don't think we're going to see anything farther than that. 4 times something can give me 35, unless it's decimal, but not. We want to use whole numbers. 9, no, 9 times something is not 35. 16 times something is not 35. 25 times something is not 25. But notice that we keep going. 36, well, this is just beyond. And 36 times something is not equal to 35 unless it's a decimal. So in this case, notice that 35, we cannot break down the number 35 as a multiples of numbers that we know what the square root of is. So in this case, for example, it cannot be simplified. Let's take a look at example F, because perhaps example F is one of those examples that you might get confused because now we're looking at variables inside the radical. But it still follows the same idea because there's an example A. 25, we were able to write down as 5 to the second. And when the exponent matches the root, they cancel out. But remember that there's always a little invisible 2 right here. And notice that the exponent is 2, the root is 2. In this case, they match out, so they can cancel out. So in this case, the square root of x squared is just x. All right. So coming back at example G, some students might be tempted to do the following, and this is something that I do want to point it out, and that is that notice that now inside we have two terms, x squared and a 1. Some students might be tempted to say, well, you know what, this 2, definitely the root is 2, this exponent is 2, so they cancel out. So now my answer is just going to be x plus the square root of 1. Because, this 2 cancels out, so it just goes out, and now I'm just taking the square root of 1. But notice that that's not okay. When we're talking about the root either cancels the whole expression or the exponent of the whole expression or nothing. We cannot just choose one of those terms. So in this case, my whole expression that is on the inside, if I take a look at a whole expression as itself, that's exponent 1. Exponent is 1, root is 2, they cannot cancel out. So in those instances, this is just one of those examples that, cannot be simplified. Now, how about if we rewrite the same expression? Same problem. But now let's put a little twist to it. How about if we put the whole exponent? How about if we put the whole expression to the second exponent? But now this is different than what we were given initially on G. Because now notice that in this case, the whole expression has an exponent of 2. So in this case, this root can cancel out. This exponent can cancel out with this root because now the exponent of the whole expression is equal to the root. In this case, they would have canceled out. And notice how different this example is from example G. Example G, the exponent of the whole expression was 1. In this case, the exponent of the whole expression is 2. Exponent 2, root 2, they can cancel out. So in this case, it would have just been square root of 2 plus 1. But I want for you to notice the difference between these two examples because I don't want for you guys to get confused with that. If we take a look at example H, if we take a look at example H, you might be tempted to say, well, you know what? The root is 2, the exponent is 3, they cannot cancel out. But notice that we can also simplify a square root of 3. We can rewrite x to the third. How can we rewrite x to the third? Well, notice that at least my objective is to write down multiplications who has an exponent of 2, because that way it will cancel out with the root. But notice that x to the third, that's equivalent to x to the second times x. Because the rule of exponent says that if you multiply, the exponents add up. But now if we write it this way and we use the same rules that we did at the initial examples that we had previously, this is equivalent to just the square root of x squared times the square root of x. And now notice that in this case, the root is going to cancel out with the exponent. And if we follow this through, this would just becomes x times the square root of x. All right, let's just take a look at 2 more examples here. Same idea here, example I. Is it possible for me to just rewrite the whole expression as an exponent of 2? Well, notice that in this case, on the example I, we can rewrite the inside as just any expression raised to the fourth, that's equivalent to just having that expression multiplied by itself 2 times. I want for you to pause and realize that this is equivalent the same. Same expression, add up the exponents, that's equivalent to 4. So this is okay for us to rewrite it this way. But what's the benefit of writing it this way? Well, if we write it this way, we can just break this down as just to the second times to the second 2. And now once we're able to just write it by itself, the root will cancel out with this exponent. The root will cancel out with this exponent. And now you have x plus 2 times x plus 2, which that's just equivalent to just x plus 2 to the second. On the last example, this is going to be one of those tricky examples because notice that here we have a trinomial. So if you want to start simplifying expressions where perhaps they're written down as a trinomial, you should be asking yourself this question: can I factor this out? Is it possible for me to factor out x squared plus 6x plus 9? Well, in this case, it is, because now x squared plus 6x plus 9, that's equivalent to just x plus 3 times x plus 3. But what's the benefit of writing this? Because now notice that x squared plus 6x plus 9, that's x plus 3 written 2 times. So that's just equivalent, or just writing it as x plus 3 all to the second. And I notice that the root matches the exponent. And when that's the case, they will cancel out. So now we just have x plus 3. So notice that all the examples that we've been doing so far, they're all about simplifying radicals. But sometimes we want to do more than that. Sometimes we want to add numbers that perhaps they have some square roots on it, or we want to multiply, or we want to divide. So let's take a look at some examples in here. As a matter of fact, I think because of the time, I'm just going to take a look at the first. Hold on, let me see how am I going to do this. So that's addition. Yeah, I'm going to choose 2 examples of addition, 2 examples of subtraction, 2 examples of multiplication, and 2 examples of division. Okay, we're not going to work on all of them. I would like for you to work on the rest. But let's take a look. These are the rules. If we want to add and subtract, we want to see if we can first simplify, and if we're able to simplify, then we can just combine like terms. For multiplications, we want to multiply the numbers that are, we want to multiply numbers with numbers and radicals with radicals. You'll see what I mean by this. And when it comes to division, if they have the same root, then we can write as one radical and then simplify. All right, let's take a look at 2 addition subtractions. Let's take a look at A. Notice that here, this is how you want to read this expression. We have 3 times the square root of 6 minus 4 times the square root of 6. Think of this as just having 2 terms right here. You're subtracting 2 terms. And just like if you were subtracting, if they have like terms, then you can definitely combine them. But notice that here, you have 3 square roots of 6, and then you want to take away 4 square roots of 6. So how many square root of 6 do you have? You have 3 square root of 6, and you take away 4 of them. Well, in that case, we will just have -1 square root of 6's. You have 3 of them, and you take away 4 of them, then you have -6. And this is what I mean by combining like terms. Note that there's 2 terms we're talking about the square root of 6's. So therefore, if they both deal with the same square root number, then you can just combine them. And the same goes with addition. We have 2 terms. Note that the first term has the square root of 15, and the second term, it's also written in terms of the square root of 15. So at this point, just ask this question. You have -9 square roots of 15, and then you add 10 of those same square root of 15. So how many square root of 15 do you have at the end? Well, in this case, we would just end up with 1. of those square roots of 15. You could also kind of see it this way as just looking at negative 9x plus 10x. Well, if we combine like terms, we would just have 1x. But now we're not just dealing with x's, now we're just dealing with square roots of 15. So if we take a look at example C, you might be tempted, well, you know what? They definitely don't have the same square roots. So negative 2 square root of 3 times 3 square root of 27, they don't have the same square roots. So I cannot combine them. Well, sometimes we have to simplify the square roots. Because now notice that under example C, my first term, the square root of 3, it can definitely not be simplified. So let me just keep it this way. But now, notice the square root of 27. 27, it's also equivalent to 9 times 3. But if we want to simplify this, we have already stated that we can just, I'm just going to concentrate all my efforts on the second term. But now notice that this is equivalent to just the square root of 9 times the square root of 3. If we use what we just discussed previously. And the square root of 9 is just 3. But when you already have a number outside after the simplification, what these two numbers are going to do, they're just going to multiply each other. And in this case, this would just be equivalent to just negative 2 plus 3 times 3, that's 9. 9 square root of 3. 9 square root of 3. I'm sorry, this is supposed to be a 3. Now notice that after the simplification, we can definitely see that they do have the same square roots. These both terms have a square root of 3. So therefore, I can definitely simplify them. You got negative 2 square roots of 3, and then you add 9 of those square roots of 3. Well, at the end, I just have 7 of those square roots of 3. Well, I'm going to let you think about example D, but I want you to think about how is it possible for you to rewrite the square root of 24? Think about it. Think about it. Let's take a look at some multiplications as well. So how do you multiply terms that are dealing with multiplication? Well, kind of like what I already stated here on the top, you multiply numbers with numbers and radicals with radicals. What do I mean by that? Numbers with numbers. So outside of the square root of 12, there's an imaginary 1. And outside of the square root of 15, there's an imaginary 1. So I'm going to multiply numbers with numbers and radicals with radicals. So I would have 1 times 1, which is 1. And when I'm multiplying square roots, I multiply the inside, which in this case is going to be 12 times 15. But notice that the multiplication, I'm multiplying 12 and 15 now under the same radical. Under the same radical. And now it's just a matter of just simplifying this. It's just a matter of just simplifying this, which is just going to become 12 times 15, so that's 180. But notice that 180, well, I mean, anytime that you're multiplying, you always want to keep asking this question. Can I simplify? Can I simplify? Well, yeah, you can definitely simplify this because now the square root of 180 can be written as 36 times 5. And the square root of 36 is 6, so I'm just going to do a shortcut. I'm not going to separate them anymore. Notice that the square root of 36 is 6, and now this just becomes 6 times the square root of 5. So yes, after multiplication, you multiply using the rules. Once you have an expression, you ask yourself, can I simplify? But in this case, we were able to. If we take a look at example F, same idea. You're multiplying numbers with numbers, radicals with radicals. There is an imaginary 1 here because there's no number in front of the square root of 5. So now we just multiply numbers with numbers. So 1 times the square root of 2, well, that's the square root of 2. And radicals with radicals. So now I'm going to multiply one single radical, and I'm going to multiply 5 times 5. And now this just becomes negative 2, the square root of 25. But we know what the square root of 25 is. The square root of 25 is just 5. So now this just becomes negative 2 times 5, which is just negative 10. So what happens if you have a distribution, just like an example of G? Well, if it's a distribution, you just distribute like if it was a regular number. Notice that here you have two terms on the inside, so therefore you want to just distribute this in. And we just want to use the rules. We just want to use the rule that we just explained previously. So let's do this multiplication, because now I want to multiply numbers with numbers and radicals with radicals. So if I would distribute to the first term, I would have 2 times the square root of 5 times the square root of 6. Well, in front of the square root of 6, this is 1. So 2 times 1 is just 2. And I'm going to multiply the inside, so 5 times 6. So that will take care of my first distribution. So if I distribute one more time, positive times a positive, that's a positive. And here you gotta be careful because we said numbers with numbers, square roots with square roots. So here I have a 2 outside, and this is just a simple 2. So I'm going to multiply just the numbers. So 2 times 2, that is 4. And the square root of 5 just carries on. And in this case, let's just simplify this. Let's not leave it this way. So 5 times 6, that is 30. All right, so that's at least how you do multiplication. Let's just do 2 quick examples for division. Under example E, notice that for example E, now we're dividing, okay? And the rule of division says if they have the same root, we can write them as one radical, and then we'll simplify. So what do I mean by that? Well, the square root of 5 times the square root divided by the square root of 3, they both have the same root. They both have a root 2. So therefore, I can just rewrite this as one big radical. So that would be the radical 5 over 3. Let me just erase this because I feel like I exaggerated that square root. So now this is just equivalent to just 5 over the square root of 3. So when you're dividing, if they have the same root, you can just divide the insides inside the square root. So the same idea here. Is it possible? Yes, but now there's a big difference here. So now that we have a 2 here. So what do we do here? Well, in this case, the way that you want to go about simplifying examples of this form is notice that the top has a 1, notice the bottom has a 2. So I can kind of just divide the numerators, or I'm not sure to call it numerators. So I can just divide the coefficients of the square roots, which in this case is just going to be 1/2. Now I'm going to multiply by using the rule that we just did here. The square root of 8 divided by the square root of 7. So that's going to be one big square root of 8 over 7. So what happens if you want to divide expressions that are a little more complicated? Just like an example of G. Well, let's see, same idea. I want to see what other numbers are on the front. Well, there's an imaginary 1, there's an imaginary 3, so this is definitely 1/3. And now, like we said, we're going to just divide the whole inside. So 15xy over 10xy to the third. So you might be tempted to say, well, you know what, this is it. That's as far as we can go. Well, notice that now we think back what we did in Algebra 1. Because now we want to simplify the insides. Well, in this case, notice that when you're dividing, the exponents count. The exponents are going to subtract. So in this case, this x is going to cancel out with this x. So that takes care of the x's. So now for the y's, if I concentrate on the y's, I have y to the first on the top, y to the second on the bottom. Whenever you're dividing, we subtract the exponents, always high minus low. So here we're going to have 3 minus 1. So that's just going to be y to the second. So let's just rewrite that. So 15 over 10, we have not touched that at all. We said that the x cancels out with this x. And now y to the first over y to the second, y to the third, that's just y to the second in the bottom, because that's where the highest variable, that's where the highest exponent is at. Uh, and at this point, we're done. At this point, we can just call it, well, we can just simplify this as this is as far as we can go when it comes to its simplification. Okay. Hopefully, with these examples, you feel a little more confident when it comes to simplifying square roots, either by just regular simplification, addition, subtraction, multiplication, or division.